In this case, there are two mirrors. Two mirrors, they are mutually perpendicular to each other. So this angle shown is 90 degree. So a ray of light that strikes two mutually perpendicular reflecting surface. So these are the mirrors. Say for example, mirror 1, and we can say this as a mirror 2. Okay. Mirror 2, reflecting surface is reflected back exactly parallel to the direction from the direction from which it came. Means if this angle is incident angle, say I say this is theta I, so this is theta r. Okay, so the first case, for the first beam of light, say in this case that this is, we can say this is the incident light, this is the incident light. Okay, so this is the reflected one. Say this angle is perpendicular, so this angle we can say theta I for the first one, and this is theta I, theta r, theta r, theta r for one. So we can say here, just replace the mirror names, mirror naming, so it will be mirror 1, this is mirror 2, and accordingly this you can say I2 and R2. So based on doing some you have to do some geometry. If you can do that, then you will find that if you use the geometry, then you'll find that the reflected ray is exactly parallel to the incident ray finally. Okay, so this is the the incident ray. We started from here initially, initiate from here. This is the reflected ray final. Okay, this is the final reflected ray. So this is the example of multiple reflection. Multiple reflection. Okay, so these are the examples where we can use the phenomenon of reflection. So in example first, the astronauts placed a corner reflection on the moon to measure it gradually increasing orbital distance. Similarly, the bright spot on bicycle safety reflectors are shown in picture 2. Okay, this is the another example where radar reflection is used. Okay, next come to the point of refraction. In refraction, light will travel from one medium to another medium, means light gets bent. So for example, say this is the media, this is the interface. Say we have media A, see this is a area, this is air A, and the other medium we have is glass, say this medium is B. Okay, and say this is perpendicular line. Okay, this is normal line. We make an angle of incidence. This is the incident ray. Okay, so we can say this angle is theta A. Okay, so light will not travel in a straight line. It goes to other medium. Okay, not traveling, so it will bend towards or away from this line, perpendicular line, depending on the medium. So this angle, say this angle is theta B. So in this picture, you see that you see that say for example, just put the name. This is A, B, and C. So in this picture, AB is incident ray. Okay, BC is refracted ray. Okay, refracted ray. and theta A is angle of incidence, and theta B is the angle of refraction. So clearly from this picture, you see that incident ray is in air, and the this refracted ray BC is not in air, in different medium. So in this example, I took the stage in glass medium. Okay, so as in reflection, we have two laws. So we can state like this: incident ray, refracted ray, okay, refracted ray and normal at the point of incidence all lie in the same plane. Okay, in this case, it's all lie in the plane of paper. And the next law we can state like this: the ratio of sine theta A over sine theta B is constant for a pair of media. Okay, so in this example, we have taken air and glass. So this constant ratio has a name. This constant is called the refractive index. So in this example, this is the in short we can say Ri. Okay, so in our case we can say here as refractive index of medium B with respect to medium 1. Okay, so in our case medium 2 is glass in our case, and medium 1 in our case is air. Okay, if this is the case, we write as sine theta A over sine theta B equals, we write eta A and B, A to B. Okay, so this is, if we don't specify which color of light, in this case, which kind of ray, so in general, if the color is not specified, we call it for the yellow light in general. Otherwise, we need to define. This means this for yellow light in general. This means this also depends on color of light. So refractive index for a pair of media is different for each color. For example, we take air and glass, it will be different for red light, different for yellow light, different for green light. Okay, so that's how we do it. Okay, let's do some math. So let's start some math. Before that, this law is also called the Snell's law. Okay, Snell's law. Let's move forward. This equation can also be written as NB means eta B over eta A, okay, equals sine theta, let's see the equation, theta A, sine theta A over sine theta B. If we don't specify any medium, then it is with respect to air. So we write with respect to what? Means with respect to air. Okay, respect to air. So in this case, we are assuming we are just taking two medium, air, and say we can take water, glass, whatever. So for example, if you take glass, then this is water. If you consider air and glass, then the glass will be the medium. It is the denser medium, and it is the rarer medium. Okay, but we have to compare with respect to what? If you consider glass and water, then glass will be the denser and water will be the rarer medium. If you consider air and water, two pair of media, air will be the rarer medium, water will be the denser medium. So rarer and denser medium depends on which pair of media we are taking. Okay, so we can simplify like this. So we can just write this as refractive index of air, medium A, with respect to air times sine theta A equals refractive index of medium B with respect to air, or the medium is the vacuum, theta B. So we see that we generally don't write with respect to air. So simply we write, if you just write refractive index of medium first, we assume that it is with respect to air. So NA sine theta A equals NB, means refractive index of medium with respect to air sine theta B. Okay, so this gives you the idea that the product refractive index and sine theta is always constant. So this is also the another statement of Snell's law. So this is also another statement of Snell's law. Okay. So this gives you the idea that, for example, say for example, if we have two media, say for example, this is the air and this is water, we can use this equation as NA, refractive index of air, okay, refractive index of air, times, say we have this angle is theta 1, and this angle is theta 2. So we can write N sine theta 1 equals refractive index of water, okay, refractive index of water times sine theta 2. Okay, so we can write this equation in this format. Let's use, based on that, we can see this as like this. If any ray passes through normal, say I'm taking media A, this is medium 2, it passes straight without bending. Okay, say for example, the other case we can take, say we have media A, say for example, this is the rarer medium and this is the medium 2 is the denser medium. If light passes from the rarer to denser, it bends towards the normal. So in this case, this angle, say theta 1, is this angle is theta 2. So from this picture, light travels from rarer to denser. So in this case, theta 1 is greater than theta 2 because light travels from rarer medium to denser medium. Let's take the other example. So this is the medium A. Okay, so now I'm taking this as this as a medium denser medium, and this medium B as a rarer medium. Okay, so for example, you can consider this is medium water, and you can consider this as a medium air. If this is that case, then if light ray enters from denser medium to the rarer medium, instead of bending towards the normal, it bends away from this normal. Okay, so in this scenario, angle of incidence is θ1, angle of refraction is θ2. So in this scenario, you see that θ1 is less than θ2. Okay, so it depends how we are going to pass the light from denser to rarer or rarer to denser. Okay, just now let's do the summary of refractive index. Okay, so here I'm representing by eta. Okay, so let's take an example. Say light will pass from air to the other medium is the glass. Okay, so we know from previous case, if light enters from air to the glass, it bends towards the perpendicular line. Okay, so this is θ1, angle of incidence. θ2 is the angle of refraction. Okay, so we can say, we can define refractive index in two ways. So we can write ng, or we can also write refractive index of glass with respect to air. If air, we don't write air. So, you know, this is the refractive index of glass with respect to air. So we know, but from the Snell's law, we can write it is sine θ1 over sine θ2. Okay, sine θ1 over sine θ2. And let's say we can also define the refractive index in terms of speed of light. Okay, so we can write refractive index of glass with respect to air. We can write as a speed of light in air over a speed of light in the medium glass in our case. Okay, so generally we write symbol, this is not a hard and fast rule, just for the symbol purpose we write C and this as a P. Okay, so we know that we can write this, just simplification purpose, we can write ng equals we know that speed is lambda naught times F. This is lambda times F. So you know that light also behaves as a wave, so it has frequency and wavelength. So this is the frequency. Frequency will be same in both media, and lambda naught is the wavelength in air, and lambda is the wavelength in water or in glass. Okay, so we can simplify like this: refractive index of glass as this F cancel out, so lambda naught over lambda. We can also plug and got that number. Okay, so let's see the other approach we are using here is this, that this is called the reversibility of light. So what does it mean? If light travels from medium 1 to medium 2, okay, so in this case, this is the incident ray, and this one is the refracted ray. Okay, So this angle is angle of incidence and this angle is the angle of refraction. Okay, in the other way around, what we can do, instead of passing the light from medium 1 to medium 2, we are passing the light from medium 2 to medium 1. So in this scenario, this will be the incident ray, this will be the refracted ray. Okay, this theta2 now will be the angle of incidence. This will be the theta1 will be the angle of refraction. We can do some math over here. So we can say, let's see, we can say like this. Here, the light travels from medium 1 to medium 2. So we can say refractive index of medium 2 with respect to 1 will be sine theta 1 over sine theta 2. Okay. In this medium, you can see here light travels from medium 2 to medium 1. So you can write refractive index of medium 1 with respect to medium 2, because light now traveling from medium 2 to medium 1. So it will be based on that, you can write sine theta 2 over sine theta 1. Okay, so you can take these two, okay, these two, and just do some simplification. Okay, you can do some simplification. Say refractive index of medium 2 with respect to 1 will be sine theta 1 over sine theta 2. And for the second picture, refractive index of medium 1 with respect to 2 will be sine theta 2 over sine theta 1. If you multiply these two, and eta 2 1 times eta 1 2, this will be sine theta 1 over sine theta 2 times sine theta 2 over sine theta 1. This gives you the relation that the product of two refractive indexes in this case is 1. So they have the inverse relation. Okay, this means 1 over 2 1. So that gives the one important concept here. If light travels from air to, say, for example, glass, okay, this means refractive index of glass with respect to air will be exactly equal to 1 over refractive index of air with respect to glass. Okay, so this concept will help you to understand the concept of reversibility of light. Means if you just reverse the path of the light, it will follow the exactly same path in the previous scenario. Okay, if you understand up to this point, then you can find the refractive index of medium 2, assuming medium 1 is air and angle of incidence is 30 degree and angle of refraction is 22 degree. Okay, so I'm referring here this picture. Based on that, you can find the refractive index of medium 2 with respect to the medium 1. Let's talk about the critical angle and total internal reflection. Before that, I will show you one demo or simulation. So in this demo or the simulation, we can see that we have two medium 1 and 2. If you change the refractive index of medium 1 and 2, say for example, I'm changing refractive index from 1 to, so now if I'm changing, you can see that this angle of incidence, this angle, may I write, say noted, this angle theta 1 and this angle theta 2, angle of incidence and angle of refraction, changes with respect to the refractive index of medium 1 and the refractive index of the medium 2. So in this scenario now, the refractive index of the first medium is 1.22, and refractive index, say refractive index of first medium is 1.22, and the refractive index of second medium N2 is 1.62. If you compare these two, based on that, this will be the rarer medium. This will be the denser medium. So if you change this refractive index, the angle will also change. So for example, you can see here, if I change the angle of this refractive index of second medium, this angle will also change. Okay. So this simulation gives you that this angle theta 2 depends on the refractive index of these two mediums. Okay. Then I could show you the other simulation. Here, this medium, first medium, let me write, first medium is air, light enters from air, then enters into glass, say for example, then again comes back in the air medium. Okay, so in this scenario, for example, the refractive index of this block of glass is 1.5. We can change that. Okay, so you see that this is the incident ray. This one is the refracted ray. Okay, this is again back in the same medium. We can call it, say, another name, say emergent ray, because incident ray and emergent ray are in the same medium. Okay, if this is the case, if light passes through a slab of glass, we are assuming the sides are parallel, then this is the original direction of incident ray. Then you see that emergent ray and the original direction of incident ray are parallel. Or in this scenario, we are assuming that the sides are parallel. This is parallel to this. This side is parallel to this side. Under that situation, these are always parallel. Okay. If you change the angle, if you change the refractive index, it will be changed accordingly. Okay. So for example, I'm changing the refractive index. You can see, even though this is the case, incident ray and emergent ray are parallel to each other. Okay. Let's start the critical angle and total internal reflection. Okay, so let's start with a picture. Say I have two media. One media is air. Okay, so and and other medium is glass, for example. If I compare these two media, this air is the rarer medium, and glass is the medium, is called the denser medium for that. So I'm calling here this as a medium A, and we are so I will tell this as a, for simplicity, this medium as medium A, glass as a medium A, and air as a medium B. Okay, now draw a perpendicular line at point. So this is the normal at this point, for this point. Okay, so if I incident light first ray, this is the ray first. Okay, then what will happen, that it will bend when you go to the other medium. Okay, so this is the, I say 1 prime. So in this case, 1 is the incident ray, and 1 prime is the refracted ray. When light travels from glass to air, if we keep increasing this angle, say now I'm increasing angle of incidence. So now raised to, if we keep increasing angle at some particular angle, this angle, what will happen? Light will pass through this media, separating the media. So now the ray will pass through the interface. So I say 2 prime. So 2 prime is also the refracted ray. So I'm just writing here, 2 is the incident ray, 2 prime is the refracted ray. Okay, so now it's passing between the interface. This particular angle, when light passes through this separating media, so this angle of incidence has a special name. This angle is called the critical angle. Critical angle. Okay, so for this case, so say I use the symbol theta c. Okay, so for, let's write here, for critical angle, so you can say theta a, angle of incidence. Okay, angle of incidence equals theta c, and angle of refraction theta b equals 90 degree. Okay, this angle is now 90 degree. Then we can use the concept of n sine theta equals to constant. This is the Snell's law. If I use this concept here, we can write this equation for both the media. For medium 1, and we can use the same concept for the medium 2, medium B. Okay, both should be equal. Okay, so NA in first medium, refractive index of first medium A times sine theta A equals, now we are in the second medium, so N refractive index for second medium equals NB times sine theta B. So in our case, NA is the refractive index of glass. So just write NA. Sine theta A is replaced by theta C, and NB times sine theta B is replaced by 90 degree. Okay, so you know that value of sine 90 is 1, so we can write theta C equals, if I do some simplification, sine inverse NB over NA. So you see that to have the critical angle, light, you can say light must pass from denser to rarer medium. So to have critical angle, light should pass from denser to rarer medium. It must pass from denser to the rarer medium. Now the question is, what will happen if we increase beyond this critical angle? Okay, so if we increase beyond critical angle, say I have the incident ray this 3, now the phenomenon called total internal reflection happens. Means light, instead of going to air, will return back following the laws of the reflection. So it will reflect in the same medium. So now it is called 3 prime. It is the reflected ray. So this angle of incidence and angle of reflection is equal. So this is called the phenomenon of the total internal reflection. Okay. So let's see, let's take one example for finding the critical angle for one medium. So say for example, as before, I take this as my first medium. One medium is water, other medium is, say for example, glass. Okay, so light, you know that for critical angle, light must pass from denser to rarer. So this angle, say theta c, in that situation, light passed through the interface. So this angle is in this case, this angle is 90 degree. Okay, so we can use the concept of the same equation that we used here. So we can write refractive index of glass sine theta c equals, now light will be in the water, so refractive index of water, then the sine 90 degree. Okay, so in general we can take this value are given. So in general, the value of refractive index of glass differs from book to book. It will be 4.5. Generally, refractive index of water will be taken 1.33. If we plug these numbers, then we'll find 1.45 times sine theta c equals refractive index of water 1.33 sine 90 is 1. Okay, so I find theta c equals sine inverse 1 over 33 over 1.45. Okay, so if you calculate, this will be critical angle will be 66.5 degree. This is the critical angle. So this is the critical angle for water glass interface, water glass media. This will be different for different media, different pair of media. Okay, so this means what? If angle of incidence is greater than 66.5 degree for water glass media, then total internal reflection happens. Total internal reflection occurs. Okay, so this means if I use the light bigger than that, instead of having reflection, it will go to the reflection. So this angle and that angle will be equal. Now it is the reflection. So this is the incident ray. This will be the refracted ray. So reflected ray, right? This will be the reflected ray. Let's draw. This will be the reflected ray. Okay. So this is a scenario. In this case, this angle theta 1 is less than critical angle. That's how we have the incident ray and the refracted ray. This is the case. The theta c here is the critical angle. More than in the critical angle, then you see theta c, the light passes through the interface. Okay, but if we hit the light more than the critical angle, then the total internal reflection happens. So this is the case of total internal reflection. This is the case of total internal reflection. So in all these cases, to have total internal reflection, refractive index of N1 must be greater than must be greater than the refractive index of second medium to have the total internal reflection. Okay, so we don't assume this case. We are not considering this scenario. Okay, so this is the case of total internal reflection. This is the example of the reflection. Okay, and other reflection, other examples we can see of the total internal reflection of the underwater swimmer image reflected back into water where the camera is going to be located. In optical fiber, we use the concept of total internal reflection. So what will happen in optical fiber, the medium, this medium is this is the denser medium, and the coating layer, this is the rarer medium. So once light traveling from denser to rarer with the angle of incidence more than critical angle, it will undergo total internal reflection. That's how the light enters from one side, will be reflected back, comes out through the reflection with the same intensity or reduced, very much less reduced intensity. Okay, so these are the total internal reflection concept we use in the optical fibers to transmit, for example, the high speed internet kind of thing. Okay, and in the binocular also we use this concept, the corner. This is the example of corner reflection, and this is the case of diamond. So how the total internal reflection happens in the diamond, this is shown in this picture. So if you understand up to this point, you can solve this problem. Before we move forward, I will show you one simulations. In this simulation, I will show you that this medium 2 has higher refractive index. So for example, I took the refractive index of, let's write, this medium, refractive index of medium 2 is, in this example, I took like 1.5, and the other medium where we are talking about, the first medium, you will see here is first medium, it is refractive index is 1. So this medium 2 is the denser medium, and medium 1 is the rarer medium. Okay, so these are, if angle of incidence is more than the critical angle, then there will be total internal reflection will happen. Okay, so you can change here this angle. If we change the value of refractive index of second medium, always total internal reflection happens. You see that angle of incident ray and reflected ray did not get changed. It depends every time will be the same. So one important concept we'll learn from the here, that to have total internal reflection, two conditions must be fulfilled. One, light should pass from denser to rarer medium, and second we want is that angle of incidence in denser medium must be greater than critical angle, for given pair of media. Okay, So once we do that, we get the total internal reflections. Okay. So based on that, you can find the total internal reflection. And if you understand up to this point, you can solve, you can solve this problem of practice 3.